So, we will continue with our lecture on bilging. In the last class, we talked about the flooding analysis, flooding and damage stability analysis. So, we will this time continue, we will finish that off, and then we will do the flooding analysis. We said that there are two ways in which you can handle a flooding or damage stability analysis. They are known as the method of lost buoyancy and the method of added weight. As I told you, what happens during flooding is that, let us assume that the ship has a few compartments. One compartment, I mean it can be any compartment or more than one compartment. Let us assume that one compartment gets flooded, means it is completely filled with water. Now, what will happen as a result is, so water fills that compartment. Okay. Now, what did we have initially? We initially had that compartment volume, okay, was okay. In that ship, what is now come? There is an added weight of water now. That is the real thing that is happening. There is a new, that is water has come into it. Now, there are different ways in which you can see this problem of flooding. We can say that, first we can say that we can do all the analysis using the assumption that the new weight, it is like a new weight that has been added to the ship. That is one way to look at the flooding problem. That is the weight of water. Water is added to the ship, and the weight is now used in calculating the final calculations. Or you can assume that this weight of the water, that much of volume, means the volume occupied by water, that much of volume is now lost by the ship. Why do we say that? See, that weight is now acting downwards. Instead of that, we can say that that much of volume is from the buoyancy, that from that much of okay. So, from that much of volume, that we can assume that much of volume is lost, that is the buoyancy lost. So, this is these are the two ways in which you approach the problem. Either you say that the buoyancy is lost, or you say that the weight has been added. So, they are known as the method of lost buoyancy and the method of added weight. So, the problem that we are going to consider is that of a box shaped barge. We have already discussed box shaped barges. You have to draw it, would be more like this. If you assume that this is the length, well, I hope I can draw it like this. Okay. Okay. So, you have a box shaped barge, it's just a box, and you are now assuming, let's, for this problem we will say that it's a box that has three compartments, 1, compartment 2, compartment 3. There are three compartments in it, and it has water filled up to a particular draft. So, water is not water, not filled, but it is now floating at some particular draft. Let us call this T initial, and this is the breadth of the vessel, breadth of this box B, and L is the length of this vessel, capital L. Now, this compartment 2 is now going to be flooded. So, this compartment 2, let us assume that the length of this compartment 2, which is this length, is small l. This is the length of this compartment which is going to be flooded. Now, what is happening is, water is entering here. Okay. So, this gets filled with water. Now, you will see that due to this water entering, buoyancy is lost, right. But still, remember, the weight of the ship, let me explain. First of all, there is a ship itself, okay, and it has components in it and weight of the ship. It has a particular weight. Now, water enters. So, it is weight of the ship plus water, weight of the water, that is the total weight acting down, or that is one way of looking at it, which is the method of added weight. in the other method you have the method of lost buoyancy, which is you have the weight of the ship as such, but some buoyancy is lost. Now remember, even when you are after it's lost its buoyancy, the ship still has to finally come to a state of stable equilibrium where the weight is equal to the buoyancy. It has to happen anyway, otherwise, I mean the weight has to be equal to buoyancy, otherwise something is moving, the ship is moving. So that is doesn't happen. So the weight becomes equal to the buoyancy anyway. Now how can this happen? Some buoyancy is lost, that means there is some more weight acting. How can that be compensated for? It can be compensated if the ship sinks a little, that means more volume comes at the top. Okay. So that means buoyancy increases, so that increase of buoyancy and the decrease of buoyancy will cancel out and ship reaches a final stable state. So that is the, so this is the initial box shaped barge, this is flooded, as a result the draft will increase, so that its final weight equals buoyancy will come. So somewhere here it reaches a final draft, T final. So this is the problem as such. Now two ways, that is in the, if you take the second way, you will see that that is the method of added weight, method of we will do both now. For one thing you can see is that the method of added weight will imply that that is in the slides in the last class I showed you that method of lost buoyancy has some points, the displacement of the ship does not change, means in the method of lost buoyancy displacement of the ship does not change, even though water is added, water is not considered part of the ship, what you are considering is that that volume is gone from the ship. So weight of the ship as such does not change, only that volume is gone from it, or buoyancy is gone from it. Now displacement does not change, as a I mean the weights are at the same position, as a result of which the LCG does not change, the LCG of the ship does not change. Similarly the other things VCG, TCG, none of those changes, TCG is the transverse center of gravity and VCG is the west vertical center, none of those things change. So it is like this in the method of, but in the method of added weight what happens is that we assume that ship is there, buoyancy is still the same, but new weight is added. It is the same concept again. Okay. I mean you are doing the same thing, in one place you are adding, one place you are subtracting, but still it is the same process. So instead of assuming that the buoyancy is lost, buoyancy is the same, but weight is added, again because of it new weight has come, buoyancy is not able to balance it, so it has to come down, process is the same, you will get the same draft. Two methods of doing it, but in the method of added weight some things will change. For instance, you will get your new displacement, the final displacement will become the initial displacement plus the weight of water added. If V is the volume of water added, rho is the density of water, then rho into V will be the weight of water added, and so the final weight of the ship will become delta F will be delta I plus rho into V. So this will become the final weight of the ship. Then similarly LCG in the final case will become LCG in the initial case plus LCG of this volume. Okay. So if you have the water added, now if you find the LCG of that water added, for instance in this particular problem we had a compartment in the middle, LCG would be somewhere in the middle of, okay, it will be in the middle, not somewhere in the middle, it will be in the exactly in the middle of that compartment. So that will be the LCG of the water weight of the water added. So that LCG into the LCG not like this, sorry, LCG of is equal to into delta initial, I wrote it wrongly, sorry, delta final. Okay, it is like this, just we are equating the moments. So delta F is the final displacement, delta F into LCG F is equal to LCG I is the initial into delta initial plus small LCG is the LCG of the weight of the water added into the weight of the water added. So this will give you the final LCG. So your LCG has now changed as a result of the new water that is added to the ship, and of course you can write similarly TCG final into delta final will be equal to TCG initial into delta initial plus TCG into rho v. So, in this case you have the transverse, and similarly you can write for the vertical center of gravity. So, this is what happens in the case of added weight. So, in the case of added weight, what has happened is that we have added new weight to the ship. That volume of water added is the weight of added, nothing has changed, buoyancy is still the same, nothing has changed in the buoyancy. So, buoyancy remains the same, but new weight is added to the ship, and so LC delta of the ship changes, that is the displacement of the ship changes, longitudinal center of gravity, transverse center of gravity, vertical center of gravity, everything changes. Then an additional thing comes, now you have, see, you have the ship, this water is now a part of the ship. Okay, you have the ship and this water is, it is like a tank containing water. Now, that means you have to consider the free surface effect, that is the movement of water. If you remember, there is a formula to calculate small I, that is the I of the tank, and then from that I there is a formula to calculate your lever, to calculate there is the free surface moment and free surface lever, that the formula was there. Now, using that you can calculate the thing is that will produce a, what will it do, free surface, what is its effect? Its effect is on GM, GM will decrease. So, the total GM, if you have to measure in this case, will be the initial GM, of course, that Kb plus Bm minus Kg, that will give you 1 Bm, 1 GM, and you have to subtract the free surface lever from it, free surface effect lever from it, and then you will get your total GM, that is your final GM. But in case of buoyancy, loss buoyancy, you do not have to do that, because what we have assumed in that is, you have assumed this volume is not part of the ship. So, that water is not part of the ship. So, there is no free surface movement. Okay. So, this is are the two, we will just do a we will see this thing, this will explain, that is the whole set of calculations that you need to do to. Now, it is the same problem. Okay. So, it is this same barge, you have a length L, barge of capital length L and breadth. So, looking at here, this capital B represents the breadth of this barge, L represents the length, capital L is the length of the barge. A compartment of length small l is bilged or flooded, damaged, water enters it, and initial draft is Ti, final draft becomes TL, sorry, final draft is TL, okay, it is defined as TL, and the other things are okay, then that is all. Okay.
The water level increases, I mean up to TL, then the water level in that one C2 compartment is also equal to.
Yes. Yeah, that is the total wall. So, what is the total amount of water that has come in? It is the water, total amount of water, if you want to put it as volume, if you look here, it will be this L into B into TL. This will be the final volume of water that will be in the compartment. Yes, correct. Then so, let us look at this, this is the way in which you proceed. Okay. So, this is using the method of loss buoyancy. So, first of all, let us find the water plane area of the of that box shaped barge. Total is L into B, and the water plane area of the lost or the flooded region is L of the flooded region is small l into B, and the water plane area of the remaining section is L minus L into B. So, this is the water plane area of the remaining flooded ship. Okay, flooded ship. Now, there is a okay. Now, there is a increase in draft. Now, the final draft TL AW into TL will give you the final volume. Okay, this will give you the final underwater volume, final that is the final displacement. Then, but note that in this particular case the weight of the ship is not v, if you assume v to be the initial displacement, weight of the ship is not changing. So, v remains the same, it is the displacement. Okay. Now, like v divided by the initial water plane area, there are two cases, one is intact, one is the damaged. In the, this is method of loss buoyancy in which del remains the same, del means it is written here as v, that del remains this v, this is del actually. Okay, the displacement. So, del divided by L minus del divided by L will give you the L divided by the initial AW, which is equal to L into B, will give you your initial T, T initial. Del divided by L minus L into B will give you your final T L. Is it clear what I said? I will write this if you want. Del divided by AW initially will give you T initial. L del divided by AW final, in this case L, will give you your T L. Okay. AWL is this, and this is A initial, AW initial, and this is AW final. Okay. Now, now the final, as you can see, the final center of buoyancy rises. It is not difficult to find the vertical height of the center of buoyancy, which we write as KBL. It will be equal to T final, L everything represents the final, TL divided by 2, that always represents the KB, that is the center of buoyancy. Now, we want to find the moment of inertia of the water plane, moment of inertia of the water plane about the center line. It will be moment of inertia, this is for the damaged case. In the initial case, remember this is actually the second part of what we did last class. Last class I took the same box shaped barge and I did all these calculations. I did all your KB, BM, I calculated I, BM, del, finally even the righting moment, we did all that. Same thing I am doing it for the damaged ship which has some part lost in it. Okay. Now, for that ship the moment of inertia of the water plane will be minus what, right, B cubed, that is this is the initial moment of inertia. If the ship is full, now what has happened, some part of the ship is gone from the ship, this is method of loss buoyancy. So, the two methods you have to very clearly understand the differences. In method of loss buoyancy, one part of the ship is not there, it is like the ship is, you know, if you look at it, it is like this now, the bottom part of the ship. So, this is not there. So, if you are taking its moment of inertia, this does not have a moment of inertia, only this much of moment of inertia is there. So, the moment of inertia of the whole thing is B cube L by 12, and B cube small l by 12 will remove the moment of inertia of that middle portion. So, this will give you the final moment of inertia B cube into L minus L by 12, and the metacentric radius becomes BML, this is the final metacentric radius, it becomes I by final I divided by del, del has not changed, del is the same. Now, you know this IL, IL is given here, del you know, we have already done this in the previous thing, we got L, del, then we can use GML is equal to KBL plus BML minus KGL. This is just the old formula. The only I wrote it very clearly in the last class, what were the important points associated with this two methods, method of loss buoyancy and method of added weight. If you just remember those, then there will be no confusion, because when you do the problems, you will see, it happens all the time, you will use some of the like some weight will be added here and buoyancy will also be lost sometimes, or you one thing or other you mix the two. So, so that what I wrote last class was very important, that is like this, in the loss buoyancy method this is same, is not changed, delta does not change, G does not change, then delta remains the same, means del remains the same, G does not change, then there is no free surface. This you should not take. You should not take the free surface effect in the case of loss buoyancy when you are doing the method. So, when you are given a problem, you do one of the methods. Okay, you the best, I will give you the formula which you can, we will do some problems, it will become clear, but in this case you do not take free surface effect, but on the other hand if you do by the method of added weight, it becomes different. Delta changes, in this delta changes, G changes, free surface effect has to be taken. These are the exact differences between the two. Okay, now in this case, in method of loss buoyancy, we got GML which is equal to, using this formula, then M R, in this case the writing moment becomes delta into GM into sin phi. Okay, delta into GM into sin phi. If you do that, you will get your writing moment. Now, actually just look at the text, you will see that they have done it for that box shaped barge with given values of L, B, T, etc. They get they do it using the two methods of added weight and loss buoyancy. They get exactly the same writing moment. So, but you will get the same only if you do this properly, means if you take the free surface effect in one case, you do not take it in the other case, and you take the way displacements everything properly, then you will get the same writing moment. So, this gives you the, this is the way in which you solve the case of loss buoyancy. Now, if you are doing the same thing by the method of added weight, it comes like this. Now, in this case the problem is slightly more simpler, in fact, that is, you have the ship, you are adding a weight to the ship, that is the problem. You are adding the water to the ship and the ship sinks. So, there is an increase in draft. In this case, let us assume that the increase in draft is delta T, and then you can see that what is the volume of flooded water. So, that is what we just said. The volume of flooded water, if you look here, is V is equal to V is equal to L into B into okay. So, the volume of water added is small l, which is the length of the compartment, into B, the breadth of the compartment, into T initial plus delta T, that is the total amount of volume, right, that is what you asked, same thing, yeah, total, there is the volume of water added. So, this will give you the now what is the now there is a change in buoyancy of the ship. Now, the ship is there, some water, weight of water is added, it sinks. Okay. How it sinks, and as it sinks by an amount delta T, which is the change in draft, and it sinks, and as a result there is a change in volume of the ship, which is delta del equals L B into delta T, where L is the length of the whole length of the ship, B is the breadth of the ship, into change in draft, that is a change difference in volume, that is a change in volume. Now, this increase in weight of the water is what is producing this increase in draft. So, they are equal, increase in volume. Okay. So, that increase in volume is equal to that increase in volume of water, or the weight, increase in weight is due to the increase in this weight. Is it clear? Increase in buoyancy rather is due to the increase in this weight. So, they are equal in magnitude, because one is happening due to the other. So, L B delta T which is the increase in volume of the vessel, L b delta T, will give you the volume of water added is L b into T initial plus delta T. Now, you can equate them, and so this will give, if you manipulate this, you will get delta T is equal to L into T initial divided by L minus L. So, this formula we will keep. Now, the final draft or the draft after flooding. So, the draft after flooding is equal to, let us write it as, in this case, T A is equal to T initial plus delta T. So, this is going to be your final draft after the ship has flooded. Now, this can be written as, so the volume of water that is added as we wrote it last time is small l b into T initial plus delta T, which is equal to T A. Okay. So, this is the fine volume of water that is added to the ship. Now, and its center of gravity, the center of gravity of this water is at its not LCG, VCG, or its kg. This is just for that water, okay. It is equal to T A by 2. This is the center of gravity of the water added. T A is the total height at which the water is added. T A is the total amount of water added, total height, divided by 2 will give you the weight of the, that will give you the LCG, or it will give you the VCG, the center of gravity of the water added. Then the displacement volume. So, the final volume, I will write del, the final volume of this flooded pontoon. So, the final volume of the flooded pontoon, the displacement volume is L B T A. Okay. So, this delta A is the final volume of the, so after the ship has, I mean pontoon means that whole vessel, okay. It is just, in this it is a pontoon, it does not matter, it is the vessel. So, when the vessel is sink, the final volume is L B into T A. This is and note that in this case we are doing the method of added weight. That means that portion is still a part of the ship, that L minus small l concept does not come here. These are the differences between the two, that should be very clear. I mean, you have to keep reading it and make it absolutely clear. Then, so the BM for this in the final case becomes I in the final case divided by del in the final case after the flooding. Now, I in the final case is the same, there is no difference, okay, because I is the same, and del in the final case we calculated, okay. This we have just calculated, it is that changes. In this case the I does not change, but del changes. In the previous case del did not change, but the I changed. At any case you are doing the same thing, but still but in this case there is an additional thing you have to take in case of added weight, because the weight of, because the water is now in the ship and it is a part of the ship, it is like that, it is almost as if we are assuming it is a tank, okay. That whole compartment is now like a tank which is carrying the water. So, that means we have to consider the free surface effect. So, free surface effect needs to be considered, and you know that the moment of inertia that needs to be considered is the moment of inertia of the compartment or the size of the tank. We assume that the whole compartment of length small l, breadth capital B is flooded. So, its moment of inertia is B cubed into small l by 12 about the center line. Now, this we have done, this is the amount of the lever arm or the amount by which the GM will change, that figures and all we have done in the previous section. So, lever arm due to free surface effect is given by in fact rho into I divided by rho into del. This is the I by del. Okay, that is a amount by which your lever arm will change, lever arm exists. So, this I you know, del A also you know. Okay. So, I is this, del A is this. So, once you know this, this much of lever arm exists, and the final Kb is the same as in previous case. It will be T final divided by 2. Okay. This is the final Kb of the ship. So, now once you have this, you need to find the final metacentric height as so, the final metacentric height can be written as Gm final case is equal to Kb in the final case plus Bm in the final case minus Kg in the final case. Actually, okay, I did not explain, okay, minus Lv. That is, note that Kg actually changes. How do you get the Kg of the final case? You can make a table like this, I mean the usual method. You have the initial weight, Kg, moment. So, first you have the initial ship, you have the weight of the ship, whatever it is, let us call it W1, and you know the initial Kg of the ship. You should be knowing, you will be knowing it. In this case, it is very simple. It is a box shaped vessel. So, you find the total volume and half of it. Okay. I mean the total depth, half of the depth, not the draft, half of the depth will give you the Kg of the vessel. So, that is the initial thing, and W1 into this distance will give you the moment. Now, water is added. So, let us assume what you can find the volume of water added, that is L into B into Ta. This gives you the volume of water added into density of water will give you the weight of water added. So, that is W2. This will give you W2, that is the weight of water added, and this will be Ta by 2, Ta by 2, this will give you this, you get the moment, and then you find the net moment divided by the net weight will give you the final LCG, final Kg. So, this gives you the final Kg. So, and lever arm we have already calculated Lv, this is due to free surface effect. Now, when you do all this, you will get the final Gm of the vessel after flooding. The only additional thing probably you have to do here is that of the free surface effect. So, it might maybe be easier to do the loss buoyancy method, it might be easier. So, we can do that also, and once you do that, you find the Mr, the writing moment using delta into Gm final into sin phi. Now, see what will happen is that delta is different in both the cases, right, means delta in both the cases means in the case of loss buoyancy and in the case of added weight, delta is different. In one case delta is the original weight of the ship, in the second case method of added weight, delta is equal to weight of the ship plus the weight of water added. Now, if that product has to become same Mr, Gm will different, Gma will be different for both the cases, okay, as a result of which the product will become same. So, okay, so that is the two methods of loss buoyancy and added weight. Okay, then okay, now what we can do is see we can write a formula like this. For instance, LBDI, I am just some notations are different. I mean last time we used, it is because of the difference in books. The other book uses T for draft, this uses small d for draft, both are draft, di represents the initial draft, db represents the final draft, that is all. This is the initial draft, db represents the final draft. And so we now have in the, remember, we are doing all these problems for box shaped vessels only. We are not going to do it for real ships, because the problem becomes slightly more complicated, because finding the volume and all that. These problems are with the box shaped barges. So here we say that what this formula says is that LBDI will give you the initial volume. Okay. Now initial volume of the initial volume underwater in the ship multiplied with the density of water will give you the weight of the ship. Okay, you know, because weight equal, using the Archimedes principle. So LBDI into rho gives the initial weight of the ship. I am just removing rho from this completely. We will just put it because it is easier to think of weight than volume. Initial weight of the ship is this. This is represents, this is the weight of water added. Rho L is the length of the compartment, B is the, in this case we just write it general. We assume that the whole breadth is not bilged, maybe only part of the compartment is bilged. So only some small b is bilged, and if db is the final draft. So what has happened? Water has entered and the ship has sunk, and it has come to a final draft of db. Therefore initial weight plus this is the, this represents the weight of water added, represents is equal to rho w into L into b into db. This represents the final weight of the ship. So all this equation represents really is that initial weight plus weight of water added is equal to the final weight of the ship. You can, when you read it, you can do it in many ways. It's means you can usually this is the what the equation represents, and it's easiest to see it in that fashion. So I explain that so that there is no confusion with the equation as such. Now we can see it as a loss of buoyancy. If you, it's not that it directly you cannot think that think of it as a loss of buoyancy. It's slightly more difficult instead of weight. So what you are saying is that this represents the initial buoyancy is equal to this is the final buoyancy minus the loss of buoyancy. Okay, at any rate this is the equation. Now I think you can just remember this equation. You should just remember this equation so that we can apply it to the problems. This equation is enough really if you want to do problems on bilging. This equation is enough. What I said before about method of, that is just to show you what the method is to be followed, but this equation is all you need. Not just know the equation, know what the equation means, like this equation, weight, initial weight plus weight of water added is equal to the final weight. Just make sure that you don't confuse these db's, di's and all that. Just that's, if you really understand, then you won't confuse it. So this is the equation that we need, and using that we can do some problem. For instance, this one, this says that, so there is a box shaped vessel which has a length of 110 meters, it has a breadth of 12 meters, depth of 8 meters, is floating at a draft of 6 meters. The midship compartment extending the full breadth of the vessel of length 9 meters. So the length of the compartment is 9 meters and it is extending the full breadth of the vessel is bilged. Now you are told that the vessel has a kg of 4.8 meters and it's floating in salt water. Now you have to find the bilged draft, GM of the vessel in the initial condition, GM in the bilged condition, and the righting moment at 1 degree of heel in conditions 2 and 3, means in the initial condition and the bilged condition. So this is a problem. Now what we can do is we just apply this formula, LBD initial is equal to LB D, not small d, LBD in the bilged condition, you can say, minus LB D in the bilged condition. So this formula if you use, in this case let us see, L is given, length of the vessel, B is the breadth of the vessel is given, then D initial is the initial draft, that is 6 meters, that is given. Now dB we do not know, okay, so this we do not know. This you are given, you are told that 9 meter is bilged and the whole breadth is bilged. So B is also the whole breadth. So you straight away, it is very straightforward problem. dB is equal to you will get 6.535 meters. So, this gives you the final draft of the vessel. So, the initial draft was 6 meters, it increased to 6.535 meters. Now, you can find the initial and the now the first question is the bilged draft that we have done. Then next one says GM in the initial condition, GM initial. Now, for that you need to find Km initial, okay, in the initial condition. Now, remember this is a box shaped vessel, you have that formula for Km. Km is equal to what was it, d by 2 plus b square by 12 d. There is this formula for box shaped vessels. So, we are talking about the initial condition or the intact condition. So, the intact means initial condition. So, Km is equal to d initial. So, this is Km initial, b is di. So, you just do this, you will get your initial Km, it gives the initial Km of the vessel. Then GM initial will be therefore Km initial minus Kg. Kg is fixed, Kg is given as 4.8 meters. So, nothing to do. So, GM, this is the GM in the intact condition. Then you are asked the GM in the bilged condition. For that you can do it this way. You can actually do it in two ways. Km, I will tell you, you can do it as Kb plus Bm, that is one way of doing it, Kb plus Bm, or you can just apply the formula. But if you do this way, Km is equal to Kb plus Bm is I by del, okay, and I, therefore, the question is what is I, and del in this case are we following loss buoyancy or Km. Well, they have followed the method of loss buoyancy. So, if we follow the method of loss buoyancy, this becomes Km is equal to I becomes L minus L into B cube by 12 divided by volume is L into B into D, okay, L into B into D, okay, D this is in the bilged condition, D final, okay, D final. So, D in the bilged condition. So, we have already calculated the D in the bilged condition. So, sorry, I think I made a mistake here. No, this will be D initial. Why? Yeah, is the question. So, see the thing is you can write it in two ways. See, that is we have seen this is the method of loss buoyancy, this is why the mistakes come. So, the method of loss buoyancy, we say that the displacement does not change. So, we are talking about the initial displacement. So, L B, you are wondering why now this will become equal to, so if I had to write it in terms of dB like you said, I would have to write here, okay, that maybe is a better way to write it, but at any rate you have to see what is the volume. Both you have to use the same concept, that is the thing, means the numerator and the denominator means I and del, it does not matter, you can use either the method of loss. See, this is a general formula, Km is equal to Kb plus I by del is a general formula, it is true for all cases because Km is equal to Kb plus Bm. Now, this I by del, when you are doing it, you have to be careful, this I by del you can do it either you do both using the method of loss buoyancy or you do both using the method of added weight. Let us take the method of loss buoyancy in this case, then I will become L minus L into this thing what I have written, and del is the original volume does not change in case of buoyancy. So, it is L B D initial or L minus L D B into D final. So, this L will cancel out and B will cancel out. So, dB. So, this will be whatever B square by, actually it will just become this B square by 12 dB, that L minus L will cancel out. So, you can just do it this way, Km is equal to Kb plus B square by 12 dB, where Kb is again it is half of that. So, it just becomes that formula only, dB by 2. So, it is just that formula, but this is, so when you do it like this, you will see what is the mistake you are thinking in the thinking process. So, in the there is only confusion in loss buoyancy and added weight. So, you do this, that will give you your Km, and then and once you have your kg, you find your gm. Okay. Then what else is asked? Okay, writing moment. Writing moment is very straightforward, nothing in it. So, you can calculate two writing moments. Writing moment you can have in the intact condition, or you can have a writing moment in the case of bilged condition. So, the writing moment is given by, so the writing moment is just the weight of the ship into the gm sin phi. So, you are asked the writing moment at 1 degree heel. So, phi is known, gm we have just calculated. You use, if you use the one for the intact condition, you get for intact writing moment, and the other one you get the damaged writing moment. Now, as you can think by intuition itself, you will see that when you have bilging, the writing moment decreases as a result of bilging. Writing moment, remember, is a tendency for the ship to come back to its original position. So, the greater the writing moment, it is like greater the ship is stable, but as the name itself suggests, when you have damaged, the stability decreases, and it is true when in this, if you look at the numerical values, you will see that the writing moment actually decreases as a result of the ship, what is that, because of the bilging or the flooding of the ship, the stability or the writing moment decreases. Other than that, it is almost same. Then note that even though you have in this case flooding, you are not going to get negative gm. That does not mean anything, means even though the ship is flooded in some point, some compartment is flooded, of course, it is in a damaged case, but gm is not negative. Gm is negative in a very extreme case. It becomes, it is a very crucial critical case when gm becomes negative, then it is highly unstable and maybe even capsizes, that is different. This does not mean anything, you will still get positive gm, the ship is still stable as such, but it is flooded, that is all. The only thing that has happened is there is an increase in draft, the ship has come down. Okay. Then this is a very similar problem. You are told that there is a box shaped vessel of length 80 meters with a breadth of 6 meters and a depth of 4 meters. It is floating at a draft of 2 meters, kg is given to be 2.2 meters. Now, in this case, a midship means center part of the ship, centraling compartment. So, in the mid part of the ship, a compartment of length 10 meters. So, that is the length small l is given as 10 meters, its breadth is 4 meters, extending the full draft of the ship, okay, is bilged. So, that the full thing is okay, that does not, that in fact goes without saying, extending the full draft. Then you are asked to find the bilged draft and the gm in the intact and bilged condition. So, at any rate, please write this formula at least in the, when you are starting this problem, at least this formula should be absolutely correct, that is LBD initial is equal to LBD after bilged minus LBD after bilged. So, this gives you the formula that you need to do these problems. In fact, I think all the problems can be solved just by using this formula, and of course, really knowing what is the method of loss buoyancy and the added weight. If you know the concept, then Otherwise, you will make errors in I and del like we did last time. I by del, that some mistake, if you take one to be loss buoyancy and the other to be added weight, it becomes a mistake. Then so once you have this, LB into DI is equal to this, you can use I think let us see, L is given, the 80, capital B is given, depth is not required, this is the draft 2 meters. Okay, so D initially is given 2 meters. So 80 into 6 into 2 is equal to 80 into 6 into dB minus LB. L is the length that is flooded, that is 10 into now in the thing, only thing that is different is that the whole breadth of the ship is not flooded, only 4 meters is flooded. So 4 into dB. So that's all. You can straight away calculate dB, which is your draft. Then rest is actually all the same thing. There is Km. Km in the this is in the you can calculate in both the cases, in the intact condition and in the bilged condition. Km in the intact condition becomes same thing, it is di by 2 plus b square by 12 di. So, this will give you Km in the initial intact condition, and you can then calculate GMI, which is your GM in the intact condition. Then you do for bilged, you will get Km, you just do Km B, Km in the bilged condition, dB by 2 plus b square by 12 dB. There is the bilged condition, you will get GM in the bilged condition. Then well, that is the only thing that is asked. So, you are asked the GM in the intact and the bilged condition, and you are asked the bilged draft. So, and actually this is quite simple in fact. So, the next problem we can't finish today. So, we will stop here. Okay. Thank you.